So today's topic, what we're going to talk about, is we're going to talk about systems of coupled bodies. We're not talking about one object by itself anymore. We're talking about an object interact with another object, two objects being interacted. Let me give you an example. We've got two blocks here. Both blocks are made out of the same material, and that material has a coefficient of kinetic friction with the contact with the table of 0.350. If we apply a force of 45 newtons onto block A, what is the acceleration of the system? Block A has a mass of 3.5 kilograms. Block B has a mass of 6 kilograms. I suggest you go ahead and get started working on this, and let's see where we go with it. My first thing is, how many objects do we have here? Two objects. Okay? So therefore, how many free body diagrams do we need to draw? Two. I'm looking around and I see 1 or even 0. And when I'm talking about a free body diagram on an object, I'm talking about an object. Okay? We have two objects of interest. We have two diagrams. So we're going to look at these objects one at a time. We look at these objects one at a time and build equations on each object. And then we figure out how to tie those equations all together. See, unlike what you may have seen in high school physics, where you pretty much memorized a number of equations for most of you, you haven't memorized equations except for that one condition, constant acceleration. Newton's second law is not an equation to memorize to solve a problem. Newton's second law is a framework to build equations to solve. So let's take a look. We start off with A. How many forces are acting on A? How many forces are acting on A? Everybody's wrong. Everybody's wrong. How many objects are interacting with A? No. No. Quit guessing. 1, 2, 5, 57. Come on, guys. That sounds ridiculous, doesn't it? Identify the objects. I've already got one for you. Namely, me pushing against the box. Right? That's our first object, me pushing against the box. We're going to label that force F. We're not going to write 45 newtons here. We're going to label that force F. What else is interacting with the box? The Earth, what's it doing? Pulling it downward, so we've got weight. We're going to label that with a W sub A. We're not going to label it with a G like I've seen some of you all do. G is not gravity. G is the free fall acceleration. I want you to label it with W. Why do we label it with W? Because how do we calculate the weight? Excuse me? Mass times the free fall acceleration. You see? Okay. Oh, one more little detail. You see the variable there? You see how the variable happens to have an arrow above it? Some of you, a lot of y'all don't put those arrows there. And what ends up happening is when you add F and W together, you think you can just add F and W together, not realizing that they're vectors pointing in different directions. You following along? It's these details that bite people in the butt. Okay, so we've got the weight pushing down on the object. What else do we have? The normal force, which is pushing up. That's going to be N sub A. Now you notice I'm putting in subscripts here because I'm looking at the weight of A and the normal force on A. What else is interacting with A? Okay. We do have a frictional force. We'll get to that in a moment. What else is interacting with A? B. B is interacting with A. Is B in contact with A? What's the direction of the force that B is exerting on A? To the left or to the right? to the left. So therefore, we're going to have a contact force from B, which is pushing to the left. Now, I've changed my, excuse me, the subscripts are telling me the object, right? Normal of A, weight of A, and so on down the line. I'm using a superscript on this one because I wanted to note that there's a force on A from B. That's what the superscript means. Okay? All good? And then there's one more force we're talking about. That's the frictional force. And that's going to be going to the left, and then we're going to label that F sub K. It's actually F sub AK, but we'll get there. All good so far? All right, what's the next thing we're going to do? Excuse me? How? How are we going to put them together? Nope. Nope. We're going to get to that. We're going to get to a free body diagram of block B here in a bit. Let's go ahead and keep analyzing A for right now. What can we do now? I've got a bunch of forces. What am I going to do with those forces? Okay, what's that going to give me? Come on, guys. If I add up, you said add up all the forces. Okay, so what's that going to give me? Which is going to give me what? Net force gives me what? Excuse me? I'm sorry, I heard it from over here. Not quite, almost, but not quite. Mass times the acceleration. In this case, we know we're going to go ahead, let's go ahead and use a coordinate axis so that positive x is to the right, positive y is to the left. Which direction is object A accelerating? To the right, okay? We're going to guess that it's going to the right. So there's going to be an acceleration to the right. We know the forces. We have an acceleration. What's the relationship between forces and acceleration? Net forces cause mass to accelerate, or net force equals mass times acceleration. So now all I've got to do is write out net force equals mass times acceleration. My vector equation. How hard is it to write this vector equation? It's not, especially if I look at my diagram where all my forces are. All I'm doing is just adding up all the forces, aren't I? The forces that I've labeled with the variables, I can take those variables and put them into my equation. This is why we have to put in that arrow above the letter, so that when we look at this, we see that it is a vector equation and not adding up variables together. All good? Everything makes sense? What's the next step? After we write the vector equation, what's the next step? No, we don't plug it in. How can we plug it in when we don't have when those are all different directions? Come on, guys. Yes? Go ahead. It can be, but that's not necessarily always true. I can screw that up by making it on a slope. If I put it on a slope, the normal force doesn't equal the weight. Or I could lift upward as well as pull forward. Yeah, but I want to do these as a general steps, because what happens if I make it more complicated? I want to have general steps that will work for almost anything. See where we're going here? What's the step I take after I write the vector equation? Yes? Break it into the components. Write the component equations. How many times have you heard me say that over and over and over again? And yet, some of y'all still don't do that because you want to break out calculators and start mashing buttons. So let's go ahead and do that. That's easy enough. What I'm doing is I'm replacing each of those vectors with a column. And each column has the x and y components. So we have F breaks down into F and 0. Weight has no x component, but it has a negative y component. So we have a minus sign pointing downward. And we calculate the weight by taking the mass and multiplying it by the free fall acceleration, thus ma times a sub g. Then the next one is the normal force, which we have strictly in the y direction. Then we have my applied force from B onto A. It's pointing to the left, so it's a minus sign. And then we have our frictional force, which is also a minus sign. We calculate friction by taking the coefficient of kinetic friction and multiplying it by the normal, mu k times n. Do you see where we're going with that? And all of that is going to be equal to ma over a. Now, to address the statement that was made a little earlier, which does apply here as well, we see that we got the normal force and the weight are pointing up and down. Now, you look at it and go, well, they cancel each other out, so I don't have to worry about it. Yes, that is true, except in your x equation, you have an n. You see, in your x equation there, you have F minus F on A from B minus mu k times NA equals MA times A. Now, if you had canceled that, if you just completely ignored the up and down forces, you would be stuck there because you don't know the magnitude of the normal force. You can find the magnitude of the normal force in the next equation, though. In the next equation, we see that the normal force is equal to the weight. And again, we already knew that, but what happens if I end up changing the slope? Then normal force is not going to be equal to the weight. It's going to be equal to the weight and something else. Okay, so now we've got two equations. How many unknowns do we have in these equations? Take a look at the first equation, the one on line 3. F minus F on A from B minus mu k times n equals m times A. How many unknowns do we have in that line? I saw 1, I saw 2. There are 3 things we do not know. We do not know the acceleration. We do not know the contact force. We do not know the normal. Having said that, we look at the next equation where we do have an expression for the normal. That allows us to get rid of one of the variables. We can now do a substitution. We can substitute MAG. Yeah, we can substitute M sub A times A sub G into the normal force. So we get F, so we get the applied force minus the contact force from B minus the frictional force equals the mass of A multiplied by its acceleration. Now, how many unknowns do we have in this equation? 2 unknowns. We can't go any far. We can't go any farther. So what's the next step, guys? Fine, no. No, more, start off a little earlier than that. What's the next step here? Do a free body diagram of object B. So looking at the free body diagram on B, it looks like this. First of all, there's B. You see we've got the arrow for weight pointing downward. We've got the arrow for the normal pointing upward. We've got the arrow for kinetic friction pointing to the left. And now we have the contact force on B from A pointing to the right. So there are only 4 forces acting on B. We had 5 forces acting on A, but we only have 4 forces acting on B. Again, oh, by the way, one more little detail. Which direction is B accelerating? To the left or to the right? To the right. So notice that the force on B from A is longer than the frictional force. It should be longer because if the acceleration is to the right, then I would expect the net force would end up pointing to the right. Draw your diagrams as best as you can. You may not be able to answer it all, but as best as you can to the right lengths. Now, having said that, the equation ends up being the same. Not being the same. We can find the equation the same way. We write the vector equation. All we got to do is go around the horn. Okay? F sub kb plus w plus normal plus the force on B from A is equal to mass of B times its acceleration. Okay, a little bit of an aside. Let's do a little physics here. Which one has the bigger acceleration, A, B, or are they the same? Prove it. Give me a mathematical proof that A and B will have the same acceleration. Yes, sir? That's not the proof. Because what we're talking about is the acceleration. We're not talking about the contact force. Okay? Come on, guys, it's not that hard. There are two kinds of proofs, right? There's the direct proof. Well, actually, there's three kinds. There's the direct proof where you go step A, step B, step C, and so on down the line. Then you've got the indirect proof where you got to kind of come at it from left field, so to speak. One version of an indirect proof is proof by contradiction. If you go through all the possible cases and eliminate the cases, what's left behind is the one that has to be true, correct? So let's try this. What if B had a bigger acceleration than A? Can that happen? Can B have a bigger acceleration than A? Why? Okay, what would happen if that was the case? Nope. Given the situation here, can B have a bigger, if B has a bigger acceleration than A, what is B going to do with respect to A? Okay. What would happen is B would pull away. If A has an acceleration, say, 0.5 meters per second squared, and B has an acceleration of 1 meter per second squared, then B would pull away from A, there wouldn't be any contact, and then there's no reason for B to accelerate. So it can't be that B has got a bigger acceleration than A. What happens if A has a bigger acceleration than B? Well, they're already in contact with each other. Well, what would end up happening is, wouldn't A kind of get squished down if A was accelerating and B wasn't? And that doesn't happen either. So that's got to be wrong. So therefore, what's left? They have to have the same acceleration. A and B must have the same acceleration. That's what I'm talking about, proof. Go through all the cases and see what makes sense. Because of that, that's the reason why my acceleration term doesn't have a subscript on it. My acceleration term is going to be the acceleration of the system of A and B together. Okay? Oh, good. So there's our vector equation. We follow up our vector equation with our component equation. The component equations, we replace the frictional term with mu k times n. We replace the weight term with m times a sub g. The rest of it is just a straight swap. Okay? When we get done with that, all we got to do is set the equalities, or set the equations. The top row becomes f on B from A minus mu k times nb equals mb times A. And the normal of B is equal to the weight of B. No surprise there. We do the substitution again for the normal, and we end up getting the final equation on block B, which happens to be the force on B from A minus mu k times the mass of B times the free fall acceleration equals the mass of B times its acceleration. Now, some of y'all got to that equation. Great. How many unknowns do we have in this equation? It's 2. We have 2 unknowns in this equation. We do not know the contact force. We do not know the acceleration. So now we have an equation that we got from block A. We have an equation that we got from block B. Now we get to play algebra. Now we get to play some algebra. Excuse me. So what we're going to do here is somehow we've got to combine these two equations. I don't want to get rid of the acceleration. That would be one way, is solve each equation for acceleration, then set them equal to each other. But I don't want to do that, because if I do that, that gets rid of the acceleration, which is what I'm looking for. So I'm going to do another trick, a third trick. What I do to one side of the equation, I have to do to the other side of the equation, right? So why don't I just add the equations together? Forces on one side, accelerations on the other side. In other words, the right-hand side of each equation add together, set that equal to the sum of the left-hand sides of each equation. You following along with me? That'd be the same thing as if I had A equals B and B equals C and C equals D, then A plus C equals B plus D. Is that going to get us anywhere? I don't know, maybe. Actually, I do know since I wrote the lecture. So let's go ahead and add the equations together and we get that expression. It looks ugly. It's not that bad. All it is variables that you've written over and over and over again. Okay? F minus the force on A from B minus the friction of A plus the force on B from A minus the friction on B is equal to the mass of A times the acceleration plus the mass of B times the acceleration. Now on the right-hand side, that actually simplifies out pretty good. We bring out the acceleration, and that makes sense. Both objects together have the same acceleration. ma plus mb equals a. Or, sorry, ma plus mb times a. There we go. But what about on the right-hand side of the equation, or left-hand side of the equation? And this is where some of you picked up on this already. Namely, that every force is an interaction between two bodies. And that whatever the force is that body A exerts on body B, then body B must exert the equal force but in the opposite direction. Thus, what is the magnitude of the force on A from B compared to the magnitude of the force on B from A? They should be the same. They are the same. Lab number 7 actually shows that. Lab number 8 is going to show that again too, but lab number 7 shows that. So, because Newton's third law, we see that the contact force between the two blocks are equal and opposite. They're going to cancel each other out in this particular equation. And that makes sense. Because if we're looking at a system of objects in this case is a bunch of objects that are being acted upon by an outside force. The internal forces are going to cancel out. So the force on A to B is going to cancel out the force on B from A. And so we end up getting this equation. And this equation, if you read the equation, you can see it. The applied force minus the friction of A minus the friction of B is equal to the acceleration times the sum of the masses. Question?
So we have for block A and block B solved for the FA of B and FB of A and
We could, but what ends up happening is because they're in opposite direction, they're going to cancel out anyway. Do you see what I mean? Because take a look if you look at the top equation, in the top equation you see that the signs are opposite. So if we keep those signs intact because the acceleration, we're going to let the acceleration be positive, then when we add those two forces together, it doesn't matter how we do it, they're going to cancel out. Okay? Newton's third law will not give us an acceleration. You following along with me, guys? Newton's third law will not give us an acceleration. Newton's second law will give us an acceleration. And thus we have to define the difference between an internal force and an external force. Let me give you an example. Okay? A good example would be a barge being pushed by a tugboat. Follow along with me? A good example would be a barge pushed by a tugboat. If I looked at the barge by itself, so if I take a look at just this big old boat right here, so there's the boat, and the tugboat's pushing in the, let's say for example, the tugboat is pushing in this direction. There's going to be a drag force due to the water. there's going to be the weight force pointing downward. There's going to be the buoyancy force pointing up. That's the drag going this way. And that's the applied force of the tugboat. All of those together are going to cause the barge to accelerate in that direction. So far, so good, right? I could do the same thing. I could isolate the tugboat itself. And I could see that the thrust of the tugboat is pushing forward, but the barge is pushing back, causing the acceleration to come off. So that gives me the acceleration of the tugboat. But what happens when I look at the system of the tugboat and the barge together? Then that contact force between the tugboat and the barge cancel out. All I care about then is the thrust of the tugboat versus the drag caused by the barge and the tugboat together. You see where we're going here? Internal forces cancel out. This is why when you walk on an airplane, it doesn't appreciably change the speed. You follow along? Okay. So now that we have all of that, now all we got to do is a little bit of algebra. Not that hard. First we find the acceleration. Now we plug in the numbers, and we come up with a 1.3 meters per second squared. Now I do realize a number of you did get this, possibly because of you've been exposed to this type of problems before. But remember, the important part I'm trying to get along here is less what's the solution to the problem, and more, how did you get that problem? How did you get that answer? Because what happens if I put a slope on this? Or what happens if I'm, like in the homework problems where we have a wheelbarrow? Or where you're pushing down and pushing forward? Or pulling up and pulling forward? Do you see where we're going here, guys? Free body diagram, net force equals whatever. Make your component equations and then solve for your unknowns. I got another problem for you. Let's see if you can work this one out. Some of you, okay, here's a question for you. I got the same two blocks. They're on the same surface, but this time they're connected by a string. If B is pulled with 45 newtons of force, what's the acceleration of the system? What do you think, guys? It's the same force, but I'm pulling on B instead of pushing on A. Why? I would suggest that you do the algebra, okay? Now, having said that, let's think about this for a moment. First of all, anybody see lab number 7 yet? Didn't think so. Lab number 7 talks about friction. Lab number 7 also talks about tension, okay? And what happens is that the external forces are still the same. The frictional forces is still the same. The applied forces are still the same. The normal force is still the same. The weight is still the same. All of those external forces are the same. What about the internal forces? Well, now the internal forces are provided by the tension of the rope. Thus, B is pulling the rope, or rather, the force on B from A is pulling to the right. The force on A from B is pulling to the left now. Does that make sense? The thing that's transmitting this force is the string itself. And what we find this by experiment, and we can prove it mathematically, not too hard, is that the tension on either end is equal to and opposite each other. And by the way, that's how a tug of war works. Yes? You're not pulling the other team. You're pulling the rope. You pull on the rope, but the rope is pulling on you. Well, what's providing the pull of the rope on you? The other team. The other team is pulling their end of the rope. And so what ends up happening is the tension on the rope is equal and opposite on either end of the rope. Follow along? So again, the internal forces cancel out, the external forces remain the same, the masses all remain the same, and therefore, we end up getting the same answer. Okay, I got 10 minutes till. I'm going to go ahead and call it a morning here. And I do have one more example. I'll leave this one as a do this on your own and let's see if you can come up with the answer. The example is this, same two masses, but we're going to pull it on a frictionless pulley. I want to know what's the acceleration of the system. I'll leave that for you guys to do. We'll talk more about that on Wednesday. Okay? So in the meantime, let's just go ahead and call it a day, and I will see you guys when I see you next.